and quantum information stuff. And this is cool. So so today we're going to continue with that. So the main thing we talked about Monday was you know, what the quantum world is like. So these are, you don't really have to worry about so much believing in quantum mechanics or anything other than it's like this computational setting for us to work with. And it's kind of a different quantum computational setting than what we're used to using. And so what the main difference is for most of what we're doing is we're going to talk about qubits. And so these are, instead of just being 0 or 1, they're a two-state quantum system, and they're described by a probability of being in either one or the other. And the wave vector itself is described by two complex numbers with norm of 1. So the probabilities are the squares of those, not the squares, but the amplitude squareds of those two complex numbers. So so that's a little bit different. It's in some sense there may be parallels with what's called fuzzy logic, where you have uncertainties to be in a bit. So you can think of a qubit in that way, maybe. So we're using fuzzy logic instead of just anything is either a 0 or 1. So so we talked about if you have a wave vector, how do you transform it into another wave vector? So that would be like if it's in a physical system, it's affected by something called the Hamiltonian, which is which tells you the way the wave vector evolves in time. But essentially, making a map from a wave vector to another wave vector, you have to preserve the norm. So it has to stay length 1, which is the same thing as saying the probabilities all sum up to 1. And so that means evolution of wave vectors is unitary. So those statements are equivalent, norm preserving and unitary. So they're unitary matrices. Or if we write everything down in terms of a basis, then a unit needs to operate. We can leave it as an operator, which is sending a wave vector to another wave vector. And that operator can also be written down as a unitary matrix, which satisfies U dagger U equals the identity matrix. So we kind of mentioned these things. So so now we're going to do something different with a wave vector. What we're going to do is measure it. So there's unitary evolution. Maybe the real world, the physical world is supposed to be described by these things that are unitary transformations. But when we, in the lab, we're taking measurements, and they get special treatment in quantum mechanics. And so that's actually kind of part of some of the philosophical difficulties with quantum mechanics. It's like, wait a minute, why is a measurement dealt with separately, and how can it really be separate if the measure is part of the world, right? So what quantum mechanics describes the physical world, then how is it that you think of measurements as separate things? Okay, so in order to do measurements, it's helpful to make what's called a projection operator. So yeah, projection operator. So projection operator in general. So let's talk about projections. So in Cartesian space, when you project, you can think about projecting onto a plane or projecting onto a line, or if it's a 2D system, you might want to project onto a line. So if I have like a point in Cartesian space and I want to project it, here's the x-axis and the y, and I'm projecting it down here, then so this point might be x hat plus y hat. That's the same thing as saying it's a vector. And if I project it down to the x-axis, it's like I'm getting rid of the y part, so I'm just sending it down there. And so if I write my vector as ax, ay, like that, a projection operator that gets rid of the y part would just look like this. Ay. And what does that give me? It gives me ax 0, like this. And so all I'm left with is this vector. So if I project this vector onto the x-axis, and then I do it again, I project it back onto the x-axis, well, it's already on the x-axis, so there's nowhere for it to go. It just stays the same thing. So if I have a projection operator and I apply it twice, I get the same thing. It doesn't change things afterwards. So that's the main thing that's useful when you think about projection operators, is you square them, you get the same thing back. And that's true. If I think of this matrix, I square this matrix, it gets back the same thing. So, so we can think of a measurement. So when you make a measurement, then you know something about your wave function, and it's in a particular state afterwards. So we can think about the process of measuring a wave function is you have probabilities for it to be in various states. After you've measured it, you pick one of those states based on the probability and you put it in that state. And then the thing that you measured is consistent with that state. So let's think about if it's a two-state system and it has two energies and you measure the energy, then you would either get the high energy or the low energy based on the probabilities of, based on the probability. The probability would tell you how likely you're to get the high energy and how likely you're to get the low energy. And then afterwards, it would be in the high energy state or be in the low energy state. And so if we're working with an orthogonal basis, like our qubit, it's either spin up or spin down, the projection operators look exactly like this. So if I have, so one of the things we talked about, the spin up state, which we also wrote as 0, and we also wrote it like this in vector notation. We had a spin down state, which we wrote as the second state, so indexing from 0, 1. So indexing from 0, then this is the second state, it's first state. But we can also write this like this. So I can define a projection operator P0, and it will look like this, 1, 0, 0, 0. And I can define a projection operator that looks like this, like that. And so now if I have a mixed state like this, or a state that's in a superposition, P1, and I apply the projection operator onto psi, it's P0 one is just going to get rid of the one, the spin down part of it. I'll just get this like that. And the projection operator to the other state will give me the other one, V1. So, so I mentioned last time that there's another way you can write a matrix out. So these are with cats like this, and you can write a matrix. Since a matrix is you're multiplying a vector, unless you can also multiply a horizontal vector to the matrix. Any matrix can be written in terms of the Ket-Frost notation. And so the P0, another way to write the P0 is this, like that. And another way to write the P1 is 1, 1. Oh, one thing I want to not forget is, so you guys remember way at the beginning of this class, there were a few lecture books that I posted on a Google Drive folder for this class on computational physics and some old textbooks. Well, I found a really nice introduction to quantum computing book and put it there for you guys. It's called A Gentle Introduction to Quantum Computing, but I like it a lot because it has lots of examples and the problems are nice in it. They're at the right level. The other, so they're looking for where is it good to read about quantum computing. That one is gentle, meaning at the right level. The one that's most upper level that I found is this one by John Preskill at Caltech. And that was great too, but I would start with the gentle one because Preskill's one is hard reading. I find it takes me a while to get through it. And then what I've been doing is I go back and forth actually. So as I read Preskill's notes, and it's like, this is just way too much at once. And then I go read the other one and it's clearer. So I'll try and post a link to it. But if you guys, there is a link on the Blackboard to the Google Drive, so you should be able to download those texts. Okay, just wanted to bring that up. So if that helps you read about or learn this material, or get it and get interested in it. So it's interesting. Okay, so let's check so that these are equivalent. So so I'm going to insert this one in here, this other way of writing it. So yeah, so let's use this, and then I'm going to show you with the matrices. So we'll just redo the calculation a bunch of times. Why did I do it up here? Projection operators. So P0 psi is, I'll use this form for it for the moment. And then it's times psi, which is A0 plus B1, like that, is equal to 0. So 0 times 0 is 1 because they're both orthonormal. So I get A. And 0, Rod and Ket with 1, those are orthonormal, so I get 0. So I get that, which is what I'd written down before, right? So let's write it the other way. So this is 1, 0, 0, 0 times AB, actually, because that's what psi is. And then we can write this 1, I get a 1, I get an A here, and then a 0 there, which is the same thing as that. So is that clear? So we do it in both ways, using this form for the projection operator, and also using a matrix form for the projection operator. So let's just do this with the other one to make everything nice and clear. So the other projection operator is this, and then we're multiplying by A0 plus B1. Please put this one out of the way. And this 1 dotted with 0 gives me 0, but 1 dotted with 1 gives me 1, and so this is equal to B1. And in the matrix way to write the same thing out, we have this times AB, which gives me 0 on top and B on the bottom, like this. Okay, and that is the same thing as B1 with this. Different ways to write the same thing out. So, so measurements are associated with, so when you have a measurement, you have a bunch of possible measurement values. Each one gets its own projection operator. And then, so the, when you think of you write the projection operators in this Bloch notation. And you can choose, like, so with measurements, what you can do is take the observed. You take some matrix that's called the observable. So usually when you're doing a measurement, there's this measurement operator, which you call the observable. You diagonalize it so that gives you a bunch of eigenstates for that matrix. So this is now throwing a little bit of jargon on here, but why am I mentioning the eigenstates? So they're all perpendicular. So you can think of, you can make them all orthonormal to each other. And then you can think of the measurement as a bunch of probabilities to be in those states. And then after the measurement, you project onto one of them with one of the projection operators. And so instead of writing out like 0, 0, you just write it out like this, where the projection operator associated with measurement in the eigenstate of the measurable is AI. And so any measurement can be written as like a sum of measurement values times projection operators. That's the idea. Okay, we're going to talk about measurement again. So you'll see this again. Yeah, we'll talk about it. So there's this basic difference. There's kind of two ways you can think about changing quantum mechanical systems. You start with a wave vector, you can either evolve it with unitary transformations, or you can measure it. And measuring is very different. So measuring it means you're choosing with a probability and then projecting it into a new state afterwards. And so that involves a random choice. And so a single thing, a single like atom or something, you measure it, it's going to acquire a new state afterwards based on your measurement. So that's different than unitary evolution, which is deterministic. There's no uncertainty involved in it. But often the dividing line gets confused because people talk about ensembles of quantum systems, and then you talk about the mean value of measurement, which is the expectation value for measuring. And so it's not necessarily obvious that that involves a probability because you're averaging over all possible measurements, right? So these are the subtleties in thinking about these things. But when you're doing a simulation, you can choose either way. You can say, I'm going to start with a wave vector, and I can involve an ensemble of wave vectors where it has some probability to be in various states. And then that's deterministic in your evolving probability distributions. Or you can say, I'll start with a single wave vector and I'll do a Monte Carlo involving measurements. And then each time you pretend a measurement, you choose this new state and project into the new state. So, so you'll see that those two different viewpoints reflected in the types of simulations that people do also. Okay, so so we keep talking about two-state atoms. So this is going to be the heart of most quantum computing settings, where you have a set of things called qubits. So I talked a little bit about a qubit before, so let's just do it again. We'll talk about the qubit again. So, and why? Because it's a building block of a quantum computer. So, yeah, so here's our qubit. Again, it's A0 plus B1. It has to be normalized. So A star plus B star has to equal 1. So here's our qubit state. It's generic qubit state. It's a two-state system, quantum system. And it's normalized. Okay. So what dimension space is this? So so A and B are both complex numbers, right? So A can have a real part of A, and we can have an imaginary part of A, and we can have a real part of B, and we can have an imaginary part of B. And all of those are, real numbers from minus infinity to infinity, kind of. Well, not really. Well, they could be, but we still have to normalize it. And there's a normalization, so that cuts down. So this is 4 degrees of freedom. And we normalize it, and so we actually have a 3 degrees of freedom. So it's a 3D space. 3-dimensional space. And we can think of it as a sphere, actually, because the normalization condition, I can write like this, equals 1. So in 4 dimensions, this gives me a sphere. So it's a 3-dimensional, but it's a 3-dimensional thing because I need 3 pieces of information to figure out where you are in the sphere. So once I give you 3, you know what the 4th one is because of the normalization condition. So yeah, so it's the 3D space, but everybody always says, well, we can think of a qubit as being on the Bloch sphere, which is a 2-dimensional sphere. It's like a regular one that you can put in real space. So there's one more degree of freedom that gets pulled out and ignored, actually. And so the thing that gets ignored is the overall thing called the global phase. So we can go back up here. So remember I talked about the probability. So the probability to be in that state is AA dagger, which is, but supposing I multiply psi by e to the I phi. So let's call it psi prime, and it's now going to look like this. 1. So the probability to be in this state is it's going to be A times A star. And so that I can write that as this start, and then these phases go away. So the probability to be in the A state doesn't get affected by this phase. And the same thing with the B one. And so, so I can treat psi prime, which is a global phase. Global means it's operating on both, the whole thing. So I could multiply a phase only on this part, and that might be significant in the sense that I'm doing operations. Then the relative phase might actually be important. But the global phase, where I just shift the whole thing by some phase, should drop out of the problem. In most situations, it will drop out of the problem. And so this is 1 degree of freedom that you could remove, and so that reduces the dimension. So instead of being 3 sphere, it pushes you down into a 2 sphere, and the 2 sphere is known as Bloch sphere. Okay, so taking that into account, so this global phase. So the whole point is the global phase should not affect measurements. Should not affect measurements. So we could ignore it. So there are interesting settings where you shouldn't ignore it. So if you start off and you're going to do an interference experiment, then you have one thing. If it acquires a global phase with respect to something else, then it's not really a global phase because it's with respect to something else. So so there are experiments where you can induce a phase by, operating on it with a magnetic field, for example, and that's like Jerry's phase, and then show that it affects interference experiments. So this is done with electrons. And there's also a polarization equivalent where you could pick up a global phase in a problem. So there's some interesting counterexamples to the we can ignore the global phase situations. But in any case, let's moving on. So so let's think about so how can we now talk about these two things? And so one way to do that is I can always remove a global phase from the problem, and so I can always rewrite the wave vector in something that looks like this: b prime e to the I phi 1, where now a prime and b prime are real. So supposing A had some phase in it, I could just remove it by multiplying by the opposite sign, opposite. So if A had some e to the I phi, and I just multiply the whole vector by the whole wave vector by e to the minus I phi, and I can remove it. It doesn't change the wave vector except to this global phase, which we just argued is not important. So, so I can always rewrite the wave function like this. And now, because it's normalized, a prime, so this is now real. So a times a star is a prime squared plus b prime squared. So b is, and b star is equal to b prime e to the minus I phi times b prime e to the minus I phi. These two guys cancel, and we're just left with those. So the normalization condition gives us this, like that. So we have one phase here, but we can say, well, what types of things obey this? And let me figure out what angle I used. I used cosines, right? Oh, actually, people like to use cosines over t. So the choice that people often use is A is equal to cosine of theta over 2. And then you're assured that a prime squared is cosine squared. And d prime is then sine of theta over 2. And this theta, the over 2 thing is a little bit confusing. So sometimes, I mean, I find it easier actually not to, not necessarily to use it, but it comes from whether you want your angles to go from 0 to pi or 0 to 2 pi. And since what we're going to do is we're going to show that we can make a map to a sphere. So if we're going to have this sphere thing, the sphere like this, which is known as the Bloch sphere, then one of the directions on the sphere is going to be like a longitude angle. So this is phi. And then theta will give us up and down. So phi is going to be like longitude and theta is going to be like a latitude. And latitude always goes from minus pi to pi, minus pi over 2 to pi over 2. And so sometimes people throw in this theta over 2 definition. I'm not sure if I did it consistently here. Did I do it consistently? I did a projection. So yeah, so one thing when we're thinking about, let's remove a global phase. So here I just said, let's assume that A prime is real. And so I took a general wave vector, both numbers could be complex. This map, where I take this and I get that, is also a projection. So if the full wave vector lived on this 3 sphere in 4 dimensions, then we're going down to the Bloch sphere, which is in 2 dimensions, a 2-dimensional sphere living in 3 dimensions. This activity of removing the global phase is also, you can think of it as a projection from this larger space down to a somewhat smaller space. And if I do it twice, of course, I'm going to get the same thing. So, you know, it satisfies that property of a projection operator. Okay, so yeah, so now let's write down the general form. And I really want, yeah, I did use a theta over 2. So I used this definition. So now let's define 2 angles. Cosine of theta over 2, 0, plus sine theta over 2 e to the I phi 1. So that's, and now we have, for every possible wave function, every possible wave vector describing a qubit, we can describe it in terms of these 2 angles, phi and theta. So yeah, so now let's take phi and theta and we'll make a Cartesian coordinate out of it. X, Y, and Z. So this is just like taking latitude and longitude and telling you where on the Earth you are in a X, Y, Z coordinate system. And so the way to do that is just this sine of theta, cosine of phi, sine of theta, sine of phi, and then we have cosine of theta. And let's be specific about the ranges. I'm sure I did this. Oh, I thought I added it. I know oh wait, yes I did. Okay, so theta is in, I did add it like that. And phi is in 0 to 2 pi. So theta acts like it's latitude or co-latitude. I guess it's a co-latitude. So with latitude, it goes from plus 90 to minus 90, but a co-latitude goes from 0 to 180. So theta is actually a co-latitude. And phi is actually like a longitude. So this is more like the standard theta for spherical coordinates that you often use in physics, rather than working on the globe where you actually work with latitudes. Yeah, okay, so now favorite states. Okay, so and if we could actually go backwards, figure out, so given any or B or A and B prime, I can tell you what theta and phi is and vice versa. So it's like unique to go back the other way, except for this projection where you lose information. So, so now there's some common states that people like to talk about, superposition states. So I'm going to make a table. So, so this, which is just our spin up thing. And what's its theta value? What's its phi value? And what's its XYZ value on the Bloch sphere? And so let's do the zero state. So this winds up being 0. This winds up being irrelevant. This winds up being 0, 0, 1. So this point, the North Pole here, that's the 0 state. And so it's pretty easy to figure out what 1 is going to be. Theta is going to be pi. This is irrelevant. So why is phi irrelevant? Well, when you're on the North Pole, you don't really care what the longitude is because it could be anything. And so so z is -1. So we can label this as 1 like that. So so there's this nice state that people like to call plus, which is a superposition state that looks like this. 0 plus 1, like that. So it's just halfway between 0 and 1. It's like been rotated. So that's the plus superposition state. And that one has theta pi over 2. And now we do care about phi because it's going to be on the equator. So it's 0, and we get, I think we get the x-axis. Actually, so we can put this here plus, and this would be x, and then we have y, or let's do x. Should I do, no, let's do x this way. X is this way, y is that way, z is this way, so then this point here would be the plus state like that. And then the y-axis is going to be I, the minus y-axis is going to be minus y, and then the minus x-axis is going to be the minus state. So let me tell you what those states are now. So the -1 looks just like the +1, but it's got a minus sign in it. Like that. So, so the square root of 2. Why am I doing the square root of 2 there? Anybody awake?
Is it for the normalization?
Yeah, that's right. So if I normalize the state, then I have to, multiply. I normalize, so you have to do a star, which would be one. Well, so yeah, let me show you how you normalize this. So plus. So I would do this a star, which would be 1 over the square root of 2 squared, plus this one, 1 over the square root of 2 squared. So that's equal to 1/2 plus 1/2, which is 1. So that's why I automatically put the square root of 2 there, because I just was like, oh, better be normalized. So it's a wave vector. The other thing to notice with these two states, this plus and the minus. Well, before we have the 0 and 1, which are the poles. So this is the North Pole and the South Pole. But they're actually orthogonal states, quantum states, because 0, when I take the dot product, I get 0 because they're orthogonal. So orthogonal states on the Bloch sphere are directly opposite each other on the other side of the globe. So when I kind of haven't told you where this one is, but you kind of get the pattern here. It's going to be the minus x-axis, so it's on the opposite side of the globe. And but when you look at this, can you tell that they're orthogonal? So if I do a plus times a minus, this will dot to that to give me 1, and this will dot to that to give me -1, and 1 minus 1 is going to be 0. So these two states are orthogonal. They're orthonormal. Or you can have a basis where I could describe a quantum state in terms of these two vectors just as well as I could use the 0 and 1 space to the vector space. So this is kind of like part of linear algebra, where you can transfer from one basis to another. So this plus minus basis is a common one, and we're going to see when we talk about what's called entangled states. We're going to see that they wind up being things look like they're in this superpositions. Yeah, so this is only, so far we've got the north and south pole, we've got two places on the equator. So there's actually two other states that are going to give me the plus and minus y axes. And these get called I and minus I. And I have to be careful about the signs for them, because so they have an I in front like this, and so if I do it this way, I like this, and there's a minus I, but I don't remember what the sign convention is. It might be that the I one has a minus sign here, and it looks like that. So I have to remember, where did I write it down? No, it's okay. It's not, in fact, so let's get it right. It looks like this. The I state looks like this with a plus, and the minus I state looks like this with a minus I here. So it's the one state has been phase shifted by pi/2 from the 0 state. So the main thing these do is they shift the phase of the down state with respect to the 1 state. And that gives you, pi/2, but we have a pi/2 here. So we want to make equal, and I'll have 0, 1, 0, and 0, minus 1, 0. So it's plus y-axis and minus y-axis. And then we have we have this direction and that direction on the equator. So the longitude goes to plus or minus 90 degrees. And this is not right? This should be 100, this should be pi or 180 degrees there, because it's the minus x-axis. Yeah, that looks good. So yeah, so these 6 are the 6, equidistant points on the Bloch sphere, and you'll see people using conventions for these conventions to describe these special superposition states. The other thing is that I minus I is also orthogonal basis, which would make sense. In fact, any two opposing points on the Bloch sphere give you an orthogonal basis that you could just describe your qubit in terms of. So yeah, so that's Bloch sphere. So transformations. So why are we worrying about transformations of qubits? So if we're going to make our quantum computer be comprised of qubits, then it's a good idea to have a feel for the operations we can do on qubits. So so some common operations, and then they get called gates, quantum gates. And then the idea is that you've got people who are trying to take two-state systems, whether they're from little microwave cavities or whether they're atoms in an atom trap or something. They're trying to make two-state systems, and then they're trying to make it possible for you to do things on those two-state systems, including being able to measure them. So you want to be able to, like, say, rotate them, or and also you want to be able to have operations that involve 2 qubits. So we'll talk about those next. But first, we'll talk about 2 single qubit gates. So single qubit gates. So a gate is something that's going to take a qubit state and give me another qubit state. So a gate, you can think of it as a wave vector to another wave vector. So it's a transformation on a wave vector. It's going to give me another wave vector. Because it has to be normalized, it's going to be a unitary transformation. So gates are unitary. So here's some examples of one. So we have the Pauli matrices. So this is the Pauli X, and sometimes it's just called the X, and this one's the Pauli Y, and this one's the Pauli Z. And in our vector notation, we can write these like this, actually. So the Pauli X is like a swap. If you look at it, it takes an up state, turns it into a down state, and the one state turns zero state, and vice versa. So you can think of this as a swap. If you want, it's not going to swap bits, but it's swapping the states. So you be careful about what you mean by swap here. But then we have the other way you can think about the Pauli X is if we're in the zero state, it's turning it into a one. And if you're in the one state, it's turning it into a zero. So it's sometimes people call it a knot. So one goes to zero and zero goes to one. So sometimes people call it a knot state. So the Pauli Y looks like this with a minus here. So the convention is there's some, so they have to be unitary, which means if I take the complex transpose, I get the same thing. That's actually not true. They happen to be your Hermitian. So there's a difference between Hermitian and unitary. So they happen to be Hermitian, which means if I take the complex transpose of this, I'll get back the same thing. To make them unitary, the check is one check is you take the determinant, make sure it's one, or length one, and but in case this one you notice that it happens to be Hermitian too, so there's a minus sign on the I, otherwise it wouldn't. So why, actually, there's a reason of why they happen to be Hermitian. So the reason it's easier to look at when you look at the Pauli Z, which looks like this. So the Pauli Z just lets you measure the spin. You get one if it's in the zero state, you get minus one if it's in the one state. So you can think of the Pauli Z as a measurement operator related with measurements for which state is it in the basis of the 0, 1 state. But we could rotate into any of these other positions on the Bloch sphere, and then the Pauli matrices would be measurement states for those. So, so since the Pauli Z is like a measurement state, it has to be Hermitian. So that's maybe another reason why when you look at the Pauli matrices, they all tend to be Hermitian. They also are all unitary. So if I took the complex conjugate transpose, and multiplied them by themselves, I would get the identity matrix. And so actually we could show that too. So if I take sigma x and I multiply by sigma x dagger is the same as sigma x because it's symmetrical. So if I do this, let's just multiply them together. So 0 times 0 is 0, 1 times 1 is 1. 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 0, 0 times 1 is 0, and then I have the last one, 1 times 1 is 1, 0 times 0 is 0, so I get a 1. So you can see that sigma x squared, Pauli x squared is equal to the identity matrix. That's the identity matrix. The same thing's true for all of them. Sigma z, that's easy to see that when you square it, you get the identity matrix. And sigma y times itself is also the identity matrix. Okay, so these are all quantum gates. So you can say, well, what do these quantum gates do to our vectors on the different parts of the Bloch sphere? And so it's I made a table in my notes. It's not all that exciting to work out, but since we wrote down what they are, you can check. So this one, it sends the zero state to itself. So the zero state's an eigenvalue. It sends it sends the one state to minus the one state. So that just multiplies it by -1. And it too is an eigenstate. Eigenstate means if you operate on it, you get some number times the state back. And then these two, if you multiply them to these, they actually transfer into the other ones, the other states. So like if I take the Pauli x and I multiply it, take the Pauli x, I multiply by 0, I get 1, and multiply them by 1, the one state I get 0. So this one actually rotates the 0, 1 bases into each other. And then this one actually gives you I states if I start with a 0 and 1. So they all so the Pauli matrices, when you apply them on our poles for the Bloch sphere, which was these and I and -I, just turns them into each other actually. And they also, the other cool thing about the Pauli matrices is they satisfy some nice, so if I take sigma x, sigma y, I get sigma z. And if I do sigma y, sigma x, I get minus sigma z. So they also satisfy various cute commutation relations that look like this. You can write this as 2 sigma z like that. So they satisfy commutation relations that are part of what's called an algebra. All right, so those are example gates, and you'll see people using these all the time when they're constructing quantum circuits. But these are just operating on single qubit. So the other handy gate that's used a lot. So there's a couple more. There's so let's the phase gate. So one thing you can ask is what's a nice way if I have any unitary transformation, any transformation from a qubit to a new state, a new qubit, say single qubit. So what's the space of all possible transformations? So this is the space of all unitary transformations. So it's a pretty large space. And you can say, I want to realize that with a quantum computer, so I need a series of gates. It's going to give me that. So there's ways to take any unitary transformation and write it into a product of a series of simpler gates. One that's popular one that's used is the phase gate in that transformation. So that's why it's kind of important. So S looks like this. I like that. So it takes the 0 state and gives a complex conjugate, it multiplies by I, the one part. So it's like takes the 0 state, turns it into the I state. So that's the phase gate. The other gate that's you're going to see just all over the place is this one called the Hadamard gate. So the Hadamard gate, and I should have written the symbols out. So the Pauli X, Pauli Y, they look like this. Pauli Z often is written like this. The phase gate's written like that. The Hadamard is written like this with an H. So when you have a quantum gate, so we have some state, and out's coming some other state. Like this. So multiply by the Hadamard gate. So what's the Hadamard gate? The Hadamard gate looks like this. And it's a -1 on this part of the vector here. So what's the Hadamard gate do? One nice thing about the Hadamard gate is if I take h times 0, I get 1 over the square root of 2, 0 plus 1, like that. So, 0 would be 1, 0, like this, 1, 0. So I get 1 times that and times the 0, and I get 1 times this on the bottom. So it takes the 0 state and turns it into the plus state, and h times 1 gives me the same type of thing minus that. So what the Hadamard does is it gives you something that's in a single state, a single thing like in your basis, and then gives you a superposition state in that particular basis. So this being the superposition of the 0 and 1. So again, you'll see people using quantum circuits with the Hadamard just all over the place. So those are common gates involving a single qubit. So we'll get to gates that use more than one qubit later. So then things will get more complicated. So now that we've talked about transformations of the I guess there's one more thing. So let's do rotations, I guess. So we were thinking about moving things around in the Bloch sphere. You kind of get the feeling that I could take any point on the Bloch sphere, and then a unitary transformation would give me some other point on the Bloch sphere. So so another way to think about unitary transformations of wave vectors for a single qubit is just rotations on the Bloch sphere. So it's a sphere, right? So that means it's going to obey the rotation symmetry group. So like in Cartesian space, in fact, there's an exact parallel, right? So if I have a point on a sphere, how do I describe rotating it to another position on the sphere? How does it rotate a sphere? So you can rotate around 3 axes, right? This is x-axis, y-axis, z-axis. The rotations don't create necessarily. If I rotate an x, then the rotate an y. I'm not going to get the same thing if I rotate y and rotate x. The other thing about rotation matrices is you can think of building them up by small transformations. So if I start moving in a particular direction, I can keep moving on the sphere. So if I think of a point on the Bloch sphere and I'm going to move it, if I want to move it over here, well, I can think of it as a series of infinitesimal transformations along some direction that's going to slowly move this point up to there. And what I talked a little bit last time about exponentials, so matrix exponentials. So matrix an exponential matrix. So if I have a matrix A, I can define e to the A as 1 plus A squared over. But I can also have, just like you would do for any exponential expansion, e to the TA would be 1 plus AT plus AT squared over 2. So when the limit of t goes to 0, I get the identity. So 1 is actually the identity. And so I can think of any matrix A sending me in some direction on this Bloch sphere, and the exponential, as I let t vary from 0 to something large, tells me how far I've gone along the trajectory. And that lets you kind of generate any transformation from local transformations. And then you can ask, what are the generators for this? And they turn out to be the Pauli matrices, so which we already talked about. So we could, if we had quantum computing system for taking the Pauli matrices and applying infinitesimals of them, then we could generate every other possible unitary transformation. So this is for a single qubit. And the question is, if I use bigger, things that are more, give me larger rotations on the Bloch sphere, can I generate any unitary transformation if I apply enough of the gates And so this is part of the like universality of computing. Can I reach any possible transformation with some recipe for generating it? And there's a bunch of theorems about this telling you what gate sets you need that will allow you to, in some limit, reach any particular state. So it's kind of some of the things that people think about. Doesn't mean it's efficient, So you could take a particular gate set for some number of qubits, and then show that you could generate any particular, at some level of accuracy, any particular desired transformation. But it may take a lot of operations, and your quantum computer may not behave well enough that you can do very many operations. So that doesn't mean it's necessarily realizable in a real quantum computer yet. But these are parts of the discussions that are going on ways to design quantum computers. So this is, maybe you could design a better gate set depending upon how easy it is for you to manipulate the bits in your actual quantum system. So not all transformations are equally easy in particular quantum systems. So just some of the things that people think about. So so now let's talk about, so these gates, unitary transformations, and then the idea is that with a sufficient number of them, a small list, you could potentially find all possible transformations for a single qubit. And then we'll build on that to then argue make the same type of argument for a larger number of bits, meaning more than one. Okay, so I'm going to put two things. So we have unitary transformations, and then we're going to have measurements. Okay. So unitary transformation. So one of the definitions of a unitary transformation is this: that if I take the matrix and I multiply it by its transpose conjugate, I get back the identity. Well, that means that U is to the -1 is equal to U dagger. Okay, so this is now the inverse matrix of that. So a definition of an inverse matrix is just this, right? You multiply it by A times the inverse matrix gives you identity. So that means U dagger is the inverse matrix. But this also means that a unitary matrix has always got an inverse, right? So they always have an inverse. So that means that it's reversible. So any unitary transformation, there's a way for me to go backwards and get back my original state. If I do a measurement, it's a projection. And so remember, we were talking about projection onto a plane. Once I project it on, I've lost this information about the y of this particular vector. And if I don't know what it is, I can't get it back. And so projections are not invertible. So they're not, it's irreversible. Another way, well, if we're talking about quantum computing, we worry about information. So there's no loss of information. But neither do you gain any, because you're not doing a measurement. So here you have loss of information or gain of information. And so the system itself is winding up winds up in a more set state, but the measurer gains information. So you can think about these things in the same way, right? So the unitary operation, it's got a state vector. It's being. I describe it with a bunch of complex coefficients, and that's where all the information is, and none of that's getting out to anybody. but it's staying in there, and I can invert it and send it back. There's always a full amount of information. Whereas if I start with a whole wave vector and I do a measurement, I project it down into a single state. I don't have any information of what it was beforehand. So if I had like psi is equal to A0 plus B1 plus C2, you know, I could have lots of states here. After I measure it, I only get one of them. I don't get, and I've lost all the information on what these A, B's, and C's were for those coefficients. Okay, so that's actually something to kind of keep in mind. So lots of information. So the there's no, if I'm evolving a wave vector, say with you, or applying applying unitary transformations on it, it's deterministic. Deterministic. So, or if I'm evolving it with a Hamiltonian because it's, you know, got interactions with something. So that means the wave vector is continually being turned in, you know, evolving with some time dependence in a very specific way. There's no uncertainty in how it's evolving. I can make transformations that tell me what the new wave vector is at every given time afterwards. Whereas when I do a measurement, you get there's a probability of getting particular values out. So this involves probabilities. So every time I do a measurement, I get a new state, but I don't know, I have to choose the new state based, or you'll get a new state based on some random probability. That's the probabilities are given by the coefficients in the wave vector, but you don't know what you're going to get out necessarily. So another thing is, so after you do the measurement, you're in this new state. So this process of projecting down into the new state, it's a fancy name. It's called the collapse of the wave function. And it can be really discontinuous. So when you're thinking about unitary evolution, if it's a Hamiltonian driven thing, it's smooth. But what the measurement, you know, instantaneously collapses you down to some subset of states. It's kind of an abrupt thing. Okay, so what else is on this list? Oh yeah, so I guess we could talk about unitary transformations a little bit more. So because they do U dagger equals I, there's some consequences of that. The determinant of U has length 1. Rows and columns are orthogonal. You can prove that. So what I mean by that is, if you look at a unitary transformation, every row is orthogonal, actually orthonormal to every other row, and every column is orthonormal to every other column. So they're kind of cute that way. And any unitary matrix can be written as e to the I h, where h is Hermitian. So you can always find this h if you want to. And another way of saying that is I could take a log of both sides. And so how do you define a log of a matrix? The same way you define an exponential. It's like the inverse operation. So you can invert that. So so this is always possible where h is Hermitian. So what about measurements? Well, so measurements are usually involved with observables. They're related to observables, which are Hermitian. So, and the reason for that is when you observe something and you measure something, you're supposed to get a real number out. And the condition for you to get a real number out when you dot it with a wave vector is that it has to be Hermitian. Okay, so let's talk a little bit about measurements now, because I haven't actually simulated, we haven't really simulated some measurements. So let's use our what's called our observable. We'll take the observable to be this Pauli Z matrix. So it's a Hermitian matrix. It looks like this. And now I'll have some wave function that looks like this. And we're going to pretend to measure it. And so let's measure it. Yeah, so if I take, so in order to decide what does it mean to measure with this as an observable, you have to say, well, what are the possible measurement values? And those are the, in this particular case, you can either get 1 or -1, and you get 1 if the state happens to be in the 0 state, and you get -1 if it happens to be in this state. So you could start with the observable, might not be diagonal, and then you'd have to find out what the preferred basis is for the measurement values. So for the sigma z, the possible values, so this is in general true for any type of measurement. You have a certain subset of possible values. And each one has its own projection operator that tells you, how you find out what state, what fraction of the wave vector is in that state. And so if I get 1, that's associated with the P0 projection operator, which looks like this. And if the measured value is -1, then I use the projection operator 1, 1. So it's convenient that my wave vector is in the same basis that the measurements are in. But I could instead just say, all right, now I have to decide, am I going to get a 1 or a -1? And so I could let's project the wave vector with this one. So if I do P0 psi, I get A, 0. And if I do P1 psi, I get B, 1. So the probability that I measure this is actually set by this. Okay, let's write it separately so it's not confusing. So if I do this, psi P0 psi, okay, I get A star. And if I do psi P1 psi, I get B star. Okay. So the probabilities for measuring 1, so the probability of measuring 1 is AA star. And the probability, which I can also write like this, and the probability of measuring a -1 is BV star, which I could also write like this. It's also 1 minus AA star. This is a 2-state system. So this tells me the probabilities. So what happens is you start with your wave function, simulate a measurement. I have to go find out, am I going to get a spin up or a spin down? So it means I have to randomly simulate this, to randomly generate a number. And if it's bigger than this, I'll say that I'm doing this state. I'm measuring a -1. If it's smaller than AA star, I can say I'm going to pretend that I'm measuring it in the the 0 state. And that will tell, and that will, then I'll decide. So I've either got a 1, I measured a spin 1, or I measured a -1. So that's how you'd simulate it. What happens afterwards? So afterwards, so you have to choose, and then afterwards, what happens? If you measured a spin 1, if you measured 1, then you have to project you have to collapse the wave function. So let's collapse the wave function. This collapses it. This is not normalized. So now I have to normalize it. So psi becomes A0, and then I can normalize it A star like that. And this is, if I don't care about the global phase, I'll just say it's 0 like that. So if you measure a -1 with that probability, then we collapse it in the other one, it becomes 1 like that. So this is kind of simple because we've only got 2 possibilities. If we had 5 possibilities, it might be a little bit more interesting. But then you might have 5 different probabilities for measuring these different things, and then collapsing it might be a little bit more interesting afterwards. And things will get, yeah. So let's write down one more thing. Is like what's another way of writing sigma z? So I said this whole sigma z was based on these projection operators, but I can write the projection operators aren't necessarily related to what value you get when you measure. And so one thing to notice is I can write sigma z. I can write sigma z as 1 times the projection operator for that projects down to the 0 state plus -1 times P1. So let's check that that's true. So it's 1 times 1, 0, 0, 0. That's the projection operator. P0 is equal to this. Plus -1 times 0, 0, 0, 0, 1. So this gives me 1 here. These two guys always do 0. And I get a -1 there. So that's the measured value. And that's a projection for that value. And here's the measured value, and here's the associated projection operator. So the reason for kind of doing it this way is we can generalize this for not for any observable. It's an observable set of projections that obey certain properties. But we can also generalize it for situations where we have. So when you do a measurement, right, we're doing a measurement, right now the example we talked about is measurement of a single qubit. But what if we have 2 qubits? Well, and I'm only going to measure one of them. So in that case, we're going to have, we're not measuring the full system, we're only measuring a piece of the system, it's partial measurements. And so this whole procedure of thinking about your projections, what does it do when you only measure part of the system? That's kind of as part of the quantum information thing, where what happens when you share information? Like, what if I take a qubit and then I put it in a superposition state that entangles it with another qubit, and then I send one of the qubits out to somebody else? What information does that person get? And what if I do things to mine? Does he see anything happen? And so this is all part of the next topic we're going to talk about, called EPR states, which are entangled states. We're 2 qubits now, and we're making sure they're correlated in how they behave so that they're sharing information. And so this then presents things like the EPR paradox and leads to things like Bell's inequalities, where should you explain the results based on hidden variables or not? And so it's like, so once you get to two qubits, which seems awfully simple, we're going to have a whole nother set of phenomena involving measurements. Only in that setting, we're going to be doing partial measurements, and we're going to talk about how much information do you have when you only have half the system. Okay, so let's write this in general. So I talked about these operator, what measurement actually is. So let's make this a little bit more general, because I did this all for a single qubit. And you could, in a two-state system, you could have like a much larger system. So we could describe, so if I start with A is an observable, what do I mean by that? It's a Hermitian matrix. Then it has a bunch of eigenvectors, and MI, the possible measurements associated with this observable are the eigenvalues. Okay, and then I can have AI are the eigenvectors. These are the eigenvectors. Okay, and then my projection operators are going to be made from the eigenvectors of the observable. And then the probability of measurement MI is psi. I think I need to do a projection. Yes, projection psi. That gives me the probability of measuring that particular value. And after measurement, psi becomes PI psi, and now I need to normalize it. So it looks like this. Actually, since projection operators, usually when you square them, you get back the same thing, you can do this. Yeah, that looks fine. So this is a little bit more general from the two-state thing where you just had -1 or -1 or -1 along the diagonal, which was the Pauli spin matrices. So that puts it in context with what you're used to if you've had quantum mechanics. Okay, so I think we're out of time. Yeah, we're out of time. Does anybody have questions? The next topic, we're going to talk about 2-qubit spaces. And then we get to cool things like the EPR paradox. Questions? So if we don't have questions, then I'll see you guys on Monday. And over the weekend, you get to look at the Metropolis algorithm, which we talked about last lecture and the lecture before. Everybody's so quiet. So I'll change the gallery. There we go. Some people are still questions. Okay.
Thank you.